So we have talked about primary structure a little bit, secondary structure a little bit, and now we're going to talk about tertiary structure, which is kind of a way of also discussing quaternary structure, because ultimately this all boils down to how did the different side chains interact with one another? How do the different R groups interact with one another? So we will go ahead and jump right into that in just a second. So anytime that you think about the tertiary structure of a protein, what you need to think about are the R groups. You need to know what those different R groups look like so that you know a little bit about the nature of the interactions. The amino acid structures are not simply, oh, I need to memorize these for the sake of memorizing them. You need to know them so that you can apply it in this sense whenever you're talking about the types of interactions that can exist and understand how dynamic they are. One of the things that we talked about here were post-translational modifications. And we spoke specifically about serine. Post-translational, I'm just going to write mods. Now, if we have amino acid 1, then amino acid 2, then we have an alpha carbon H, CH2, OH. That would be an example of a serine residue within a polypeptide chain, and we'll call that 4 and ongoing. Okay, now when you look at this R group for serine, one of the things that you should recognize is what are the good types of interactions that it could be involved in, or what are the interactions that it could easily be involved in? Well, one thing that you need to know is that this is a great candidate for hydrogen bonding. It has that hydroxide group right there, but this can undergo some changes, and one of those is by protein kinases. I'm just going to write PKs. What they can do is they can take a molecule like ATP and transfer a phosphate group to it, and they will be left with ADP, and now you have a different look to your serine residue. Your serine now looks like such. Here's our alpha carbon, CH2, O, P, O, O, O. Okay. That serine residue that was a great candidate for hydrogen bonding now all of a sudden has 2 negative charges on it. Can it still be involved in hydrogen bonding? Yeah, it probably can. But now you've opened the door for it to be involved in some sort of ionic interaction. Likewise, think about the number of charges there. You have 2 oxygens, 2 negative charges there, so they can attract 2 positive charges. In addition to that, now I know that this is not the best representation, but we've drawn this R group in that space. Now, whenever we have it modified, it's nearly 3 times as tall. And I understand I didn't really measure that out, and the scaling might be a little bit off, but know that you have an R group that is filling a different amount of space than it previously did. In addition to that, one of the things that you can see, and I illustrated this a little bit, and I talked about different amino acids next to one another and how they'll have an impact on their pKa values. And I believe that I mentioned that the pKa values go down when in reality they go up. The point of that, what I wanted you to take home from that, was that pKa values of adjacent residues are going to vary. So if you have 2 aspartic acids next to each other, they're not going to have the exact same pKa value. One might be higher than the other. That was the point of that discussion in class. All right, so you have to be familiar with post-translational modifications because these different R groups are going to interact differently whenever they're changed. And overall, when you're talking about the tertiary structure of a protein, you have to be familiar with what those R groups are and how they interact with one another. Now, the next thing that I want to talk about is actually jumping ahead a little bit in our lecture. I wanted to talk about protein folding and refolding. Now, one of the people that I mentioned several times during all of this is a fellow by the name of Christian Anfinsen. Now, he did some seminal work in protein folding and refolding. A-N-F Anfinsen. And he did work on a protein known as RNase And what he did was he said, all right, well, I have this very pure protein, RNase A. There we go, there's our pure protein. What I want to know is how the structure is related to the function. And I also want to know basically, if I disrupt this protein, if I take it from that 3D folded structure to a linear, denatured structure, well, I know that this works, this is functional, this does not work. But what if I could get it to go back into this 3D structure? Would this work? And the work that he did was to basically illustrate that yes, indeed, you could do that. So he unfolded a protein, and he did that by treatment with dithiothreatol, so DTT, so he broke up any disulfide bonds. Then he heated it up, put it in, I can't remember, it was a extreme condition, so either acidic or basic, and then he titrated or removed all of those things. He titrated all of those things away, and he was able to get this protein to refold and be functional again. So that was great work because it showed a correlation between structure and function, but also you can break the protein and you can repair it, more or less. So with that said, I wanted to mention that that's just a valuable exercise, because now what that means is that if you want to purify a protein, you can unfold it and help purify it and then refold it, and it's functional again. So keep Christian Anfinsen in mind. He's an important figure in all of this research. Now, in addition to all of that, with respect to protein folding and refolding, one of the things that I wanted to mention, and one of the things that we talked about, was the GRO-EL-ES complex. We also talked about chaperones, and specifically we talked about HSPs, heat shock proteins. These are proteins that basically assist in the folding of a partially folded or a misfolded protein. So these guys will take something that is partially folded and finish the job, and they will fold them. In addition to that, so look back at your notes, look back at the PowerPoint presentation as to how that is done. The GRO-EL, GRO-ES complex does it in an ATP dependent manner. So it will bind an unfolded protein as well as some ATP. It will hydrolyze, I believe it's 7 ATP molecules, refold a protein, and then as soon as it's ready to release that properly folded protein, it will bind onto another misfolded protein. I also made mention of PDI, protein disulfide isomerase. This is a protein that recognizes where there are incorrect disulfide bonds, so bonds between two cysteine residues. What it will do is PDI will take this protein right here and it will refold it so that now it looks a little bit more like this. So we have the disulfide bond between this residue and this residue, rather than this residue and this residue. So protein disulfide isomerase, well, it isomerizes disulfide bonds. So these are all some examples of important proteins that I want you to be familiar with for proper folding of polypeptide chains. All right, well, thank you very much. I hope that this was informative, and have a good afternoon.